Hello, welcome to everyone. In the yesterday's class, we completed the applications of Gauss law. Okay, in today's lecture, let us study about the electric field and electric potential. Okay, yeah, the outline of today's class is as you see in this slide. Yeah, electric field. Next, conservative nature of electric field. Next, irrotational field. That means irrotational nature of electric field. Next, let us give introduction to the electric potential. Okay, right. First, let us go for the electric field. Okay, now let us start with the electric field. We already studied the electric field, and we know the formula of the electric field of a point charge. Okay, let us briefly discuss about that introduction. Yeah, first thing is electric field or electric field intensity, capital E. Capital E. Okay. Yeah, what is the electric field? Wherever you have some static charge, there you always find the effect of that electric charge in and around that charge. Okay. That effect is given by the concept called electric field. Okay. Suppose that there is one positive charge, whatever it may be, the positive or negative. So whenever you place one test charge around this charge, in the immediate vicinity of this charge, okay, if you are putting plus 1 coulomb test charge, then what happens? The effect of this charge is felt by this unit charge. That's why this unit charge moves away from the charge, from this charge. Okay, external charge. What's the meaning of that? Why it is moving? Why the test charge is moving away? Why? Because in the place where we have placed the test charge, there is some influence of the external charge. That may be plus Q coulombs. So, this area in which we place the test charge is called as the field of this Q coulombs of electric charge. Okay, that's why, because we cannot see anything in between that charge and this charge. That's why then we get one doubt that how this charge is influencing the test charge. Okay, to get some physical picture of that, we imagine some field between those two charges. We imagine the test charge in the area of influence of the external charge. That area of influence of the external charge is known as its electric field. Okay. Suppose that the field is extended up to this line. Okay. Now, the field intensity may vary from point to point in the electric field. Why? Because some points are away from the positive charge, some points are very near to the positive charge. Okay, because whenever you place this unit charge at these nearby points, the influence felt by that charge is more compared to the influence felt by the same charge when placed at the farthest points in the field. Okay, that means electric intensity at one point, point 1, is different from that of the electric intensity at the point 2. See, if the field is same everywhere, then we call that field as a uniform electric field. That is different thing. Okay. Usually, field at one point will be different from the other point. Okay. See, what is this at point 1? Let us call the electric field E1. E1. At point 2, let us call the electric field E2. Field at point 1, field at point 2. We also call E with another name electric field intensity. Actually, it sounds good. Electric field intensity. What is E1? Electric field is there at both point 1 and point 2, but its intensity is varying from point 1 to point 2. That's why we call E1 as electric field intensity at the point 1. We call E2 as the electric field intensity at the point 2 in the field. Okay, both points are located within the field. So, what is the other name for the electric field? E, electric field intensity. Okay. What is the formula for the electric field of this external charge, external point charge? Okay. See here, we take this distance between the external charge and test charge to be R. Okay. To be R. Now, electric field is nothing but, we know that electric field is nothing but the force acting on a unit positive charge. Okay, electric field or electric field intensity is nothing but the force acting on a unit positive charge. Okay, so in this case, the force acting on this test charge is nothing but the field of the external charge. Okay, field of the charge Q. So, in this case, according to the Coulomb law, force between these two charges, one is Q coulombs, other is 1 coulomb, then the force acting between them is given by 1 by 4 pi epsilon naught. 1 by 4 pi epsilon naught. Okay, I will write here. Yeah, F is equal to 1 by 4 pi epsilon naught Q into 1 charge is Q, other Q coulombs, other charge is 1 coulomb. So Q into 1 by R square. Why? Because this distance is R. So this is nothing but this is equal to 1 by 4 pi epsilon naught just Q by R square. Actually, according to the Coulomb's law, this is F. No. But what name we are giving for this F? In the case of one of the two charges is 1 coulomb, this is nothing but E. So this is equal to E. Here F is equal to E. So formula for the electric field of the point charge Q is given by E is equal to 1 by 4 pi epsilon naught Q by R square. So this is nothing but the force acting on a unit positive charge placed at the distance R from the plus Q coulombs charge. So what is the formula for the electric field of a point charge? General formula: E is equal to 1 by 4 pi epsilon naught Q by R square. Okay, this we know, right? Here you see on the slide, this is E is equal to Q by 4 pi epsilon naught R. or 1 by 4 pi epsilon naught q by r square. Okay, this is about the these are the primary things we already covered in the previous classes. Okay, again I am recalling those points now in order to study the conservative nature of the electric field. Okay. Yeah, next we are going to study the conservative nature of the electric field. Yeah, conservative nature. Conservative nature conservative nature of conservative nature of electric field. Conservative, okay, nature of electric field. Conservative nature of electric field. Okay, so you know that fields are of two types. Any field, that may be magnetic field, that may be any field. Okay, mechanical field, velocity field, temperature field. So how many types of fields are there in the physics? There are two types of fields. One is scalar field, other is a vector field. Scalar field, next vector field. So how many types of fields are there? Two types of fields. One is scalar field, other is a vector field. What is scalar field? In scalar field, we can ascribe to each and every point of that field only a scalar quantity. If you go for the vector field, you may define at each and every point of the field direction and the magnitude of a vector. In the vector field, at each and every point you may attach one vector. Vector means it is having both magnitude and direction. If it is a case of scalar field, at each and every point, of that field, you can assign only one scalar number, one quantity, magnitude of one quantity, scalar. You can attach at each and every point of the scalar field a scalar quantity. If it is a vector field, you can attach at each and every point of the field a vector. That means you are taking a physical quantity which is having both direction and magnitude. In case of scalar field, you are choosing a physical quantity which is having only magnitude. The question of the direction does not arise for that quantity. Okay, in scalar fields. Okay. Now, we are talking about electric field or electric field intensity vector. So here This field is a vector field. This field, electric field, is a vector field. What is the meaning of that? At each and every point of that field, you may define electric field vector. Electric field vector. At each and every point of the field, you have to show the direction of electric field. You have to give the magnitude of the electric field. Okay. The magnitude is same, that is the special case. Magnitude is there. In addition to that, direction is also there. If it is also same, but the magnitude and direction are also the same, then what do you say about that field? That electric field is a uniform field. Uniform electric field. If any one of these two qualities is changing from point to point, then you call that electric field is not the uniform field, or the electric field is not uniform in that area, okay, in that field. This you have to remember. What is the meaning of uniformity? What is the meaning of sameness? The sameness applies to both the qualities, direction of the vector as well as the magnitude of the vector. Okay. Suppose you take a particle or a planet rotating about the sun. Okay, this is the case. Take one example. Here, what is happening here? A particle is, okay, the planet is encircling the sun. This is a planet revolving around the sun. Okay, revolving around the sun. Okay. Now, what happens here? So you see, this object velocity. See, this rotates with some orbital velocity. Okay, this is same. But here, its direction is always changing. Its direction is always changing. Direction is changing. For this object, direction is changing. So, we say that here the velocity is changing. Why? Because direction of v is changing from time to time. Okay. Right? Yeah. So whenever you are taking a vector, its magnitude may be its magnitude as well as the direction has to be same in order to say that the vector is not changing with the time. The quantity is not changing with the time. Okay. Right. This is about the change of a vector. Change of a vector. It is something special compared to the case of change of a scalar. Change of a scalar. Okay. Right. Here our electric field is a vector. Our electric field is a vector. That's why at each and every point of the electric field, we have to give the direction and magnitude for the electric field. Right. Now, what is the nature of this electric field? What is the nature of this electric field E? Electric field E. What is the nature of the electric field E? Okay. Now, we want to study about this. Yeah. See, there is another type of classification. Fields may be conservative fields, may be non-conservative fields. There are two types of fields: conservative fields non-conservative fields. Okay, here what is the definition of the conservative fields? You already know that. We may classify the fields again into two categories. That field may be conservative field, that field may be non-conservative field. Okay, some friction fields. These such fields are non-conservative. Why? Non-conservative fields. Yeah. Suppose that you want to. Suppose that this is some area in which you find the electric field. Electric field. Yeah, here this is a range of the electric field. You find the field, okay, inside of this line, this border line. Okay, yeah. Here you are taking 2 points. Here you are taking 2 points, A and say this is 1 point. Okay, this is some another point. You are taking 2 points here in the electric field. So this is 1 point here. Say this is A. Say this as B. Say this as B. There are 2 points. Okay, A point and B points. Okay. Now you want to take the charge from this point to this point, this point to this point. Now you may take the charge along this path. Okay, along this path. Okay, you may take the particle along some different path 2. Say this as a path 2, this as a path 1. This is a path 1. Okay, this is a path 2. Some different path. This one is some different path. This is first path. Okay, this is second path. A to B. Okay, you want to take the particle from from A to B in 2 paths. Somebody is taking the charge along the first path in order to reach B. Somebody is taking the charge along the second path to reach the B. See, both paths are different. What we have to check here, yeah, charge is moving. That means some force is acting. Which force acts in the electric field? Electrostatic force acts in the electric field. So electrostatic, by the action of the electrostatic force, see, once the particle is moving through path 1, once that particle is moving through path 2, then we calculate the work done in the both cases. Work done in the both cases. Work done to take the charge along the path 1. Work done to take the charge along the path 2. Along the path 2. See, if these two works are same in the magnitude, then we call the field present here as conservative force field. In conservative field, conservative forces act on the charges. See, in case of electric field, work for path 1 and work for path 2 will be the same. That means here work done to take the charge along the path 1 is equal to work done to take the particle along the path 2. Both things will be the same. Okay. So work does not depend on the path. Work does not depend on the path. Work is path independent. Such fields are called conservative force fields. Our electric field is a conservative field. Why? Because these two works are same. Work is path independent. But it depends on, for conservative fields, the quantity of the work depends on only the initial point, initial position and final position of the charge. Work is directly proportional to these things. Work depends on initial point and final point. Initial point and final point. Okay, but it does not depend on the path. Why? Because you may connect the 2 points with innumerable paths. You may move the charge one among all those paths, but the work done is the same. Okay, you may choose any path, but the work done is the same as long as you does not change the initial and final positions. Okay, initial and final positions. Okay, right. Yeah. So our electric field is a conservative field. So this is the inherent nature of the electric field. Okay. Suppose that what I am saying, W1 is equal to W2. W1 is equal to W2. W1 is equal to W2. W1 is equal to W1 is equal to W2. Okay, W1 is equal to W2. That means both work done in both cases is same. Suppose that you are moving the charge from A to B, then B to A, then B to A. Okay. Here, in order to move the charge from A to B, how much work is done? Say W1. If you want to bring the particle back to the path A, we have to do the same work in the reverse direction. So what is the total work done in this case? What is the total work done in this case? Okay. W1 and W2 are same. Okay. Here you are adding W is equal to W1 plus minus of W2 plus minus of W2. Okay. Here W1 minus W2. W is equal to W1 minus W2. Okay. Since W1 and W2 are same in the magnitude, so you get W is equal to W1 minus W1. So this is 0. So the total work is 0. The total work is 0. So for one circulation of the charge, that means from, you see on the slide, A to B and again B to A, the total work done is 0. The total work done is 0. For one circulation from A to B and B to A, the total work done is 0. So you may define the conservative field like this also. If the total work done to move a particle in one closed path is 0, then the field is called as the conservative force field. Okay, you may also define the conservative force field in this manner. The meaning is same. Okay, the meaning is same. Right. This is about the conservative nature of E, electric field. Yeah. Here you see in the slide. Yeah. You see here there are 2 points, A and B. 2 points are there. See how many paths are there? Yeah, this is one blue line, green line, red line. You may move the charge from A to B in 3 ways: along this blue line, or along this red line, or along this green line. Okay. But finally, for all these 3 paths, the initial point and final point are same. So, the work done to move the charge along this green path is equal to work done to move the charge along this red path is equal to work done to move the particle along this green path. In these 3 cases, work done is same work, same effort is needed to bring the particle from A to B, whichever may be the path. That means our E is a conservative force field, or conservative field. E is a conservative field. Okay, the amount of work is same as long as you do not alter the positions of A and B. That means the work done does not depend on the path or the shape of the path, but it depends upon the positions of initial point and final point. Okay, right. Yeah, this is about the conservative nature of the electric field. See, in non-conservative field, this does not happen. Okay, if you are taking the instead of electric field friction field, then what happens? Here, that depends upon the surface. So, when you take one path, the work needed is something. When you take other path, the work needed may be different from that. So, the friction changes from path to path. That's why we cannot call the friction field as conservative field. Conservative field. Why? Because the work done directly depends on the path. Even though initial and final points are same, if you take a different path, you have to do some different work. That's why such fields are known as non-conservative force fields. But our electric field is absolutely a conservative force field. Conservative force field. But so far, we just discussed the qualitative nature of this conservative nature of electric field. How to write a statement in the mathematical form. For a conservative field, how to write a statement in the mathematical form. I would write one mathematical equation to describe the nature of conservative nature of the electric field. How to express that? See, what is the electric work? Work is equal to W. What is the definition in mechanics? What is the definition in mechanics? W is equal to F into S. W is equal to F into S. Okay. Here, for maximum work, we just simply write F as displacement is in the direction of a force. Okay, right. Here, for example, let us take only unit positive charge. Then this F becomes E. Your F becomes E. Okay, your F becomes E. Okay. Next dot. This is L, distance, L or R. Otherwise you take L, okay, E into L. Okay, L is the length of that means distance between the initial point and a final point, E dot L. Okay, if this is infinitesimal length, then what you have to do, if you divide the path into small segments, you have to put integral. So what is the formula for the electric work? Integral E dot dl. Integral E dot dl. Yeah. This is, so what is the formula for W? Electric work, electric field into distance at the path length R. You may write this as a integral E dot dl. That means E is a electric field, L is the distance. So force into distance is equal to 1. So instead of F dot S, here you have E dot L or E dot dl integral or integral E dot dr or dl. So here this integral refers to from A point to B point, from A to B. Integral A to B, E dot dl. Okay, this gives you the electric work. This gives you the electric work. Right. Now, suppose that you are getting some value for E dot dl. You are getting some value for E dot dl. After doing integration, suppose that you are getting some value 5. You are getting some value 5. This is A. Okay. This is A, lower limit A, upper limit B. Integral A to B E dot dl. Integral A to B E dot dl. Integral A to B E dot dl. So suppose that this integral value is say some phi L or phi R, function of distance. Okay, it's a scalar function. See, then you have to substitute the limits A to B. No? So then what happens? What happens for this work? Work is equal to phi. See here, either it may be A to B or B to A. It becomes phi B minus phi A. Phi at B minus phi at A. If you are taking the work from B to A, work done to move the particle from B to A, see the slide. Here you have psi A. Here this is B to A, na? Psi A minus psi B. So total work you are getting 0. But if you consider the work done to take the particle along any one path, what you are having here difference of this scalar quantity. Okay, psi B minus psi A or psi A minus psi B. Okay, so your work you may define the work as a decrease in some quantity, scalar quantity known as phi. Okay, we call this phi with the special name potential. This is okay. Here, electric field is sufficient to describe the field of a charge. But again, we are introducing some auxiliary quantity, potential field, not a potential. Okay. See, where do you find the potential for every conservative field? For every conservative field, you have electric potential. So we call this as a potential field, this quantity. Okay, right. We call this psi r as a potential field. So your conservative field is a potential field. Okay, what's other name for conservative field? Potential field. You do not find potentials for the non-conservative force fields. Non-conservative force fields. Okay, you can only have the potentials, scalar functions exist for these conservative forces only. That's why we call conservative force fields as potential fields also. So we are introducing one more physical quantity in electrostatics, that is electric potential. So I just told you that how it is arising. Whenever you are calculating the electrostatic work, then you are getting the difference of this scalar function. So what is potential? Is nothing but the electric work. Is nothing but the electric work. That you know already. You know that you are already familiar with this word electric potential. It is not the new one. Yeah. Next, then what you are calculated actually, work means integral work is equal to integral EDL. Total work this is. How much this is? You have seen the previous slide. This is 0. This is 0. So what is the mathematical statement of the conservative nature of the field? Integral, closed integral. See there, not this one. Integral with this symbol. So integral along the closed curve of E dot dl is equal to 0. This is called the circulation of E is 0. E dot dl for a closed curve is 0. Okay, this is a mathematical statement of the conservative nature of the electric field. What is that statement? Circulation of vector E is 0. That means linear integral along the closed curve of E is 0. E is 0. Okay. So the linear integral along the closed curve for the electric field is 0. So integral E dot dl is equal to 0 is a mathematical statement of the conservative nature of electric field. So we want to write one more mathematical form for the conservative force field. So here this is irrotational. Electric field is also called as a irrotational field. To pronounce this, to say this, we restate the mathematical statement of conservative nature of electric field in order to show the irrotational nature of the electric field. Okay, so but here this statement is equivalent to the previous statement. E dot dl is equal to 0. Okay, see whenever a field is called as a rotational field, then you have one mathematical statement: curl E is equal to 0. Curl of that E is 0. Curl shows you the rotation of a vector. Here our vector is E. See, the rotation of the vector E is 0. The rotation of the vector E is 0. That's why it is called as a irrotational field. So, what is another statement showing that E is a rotational field? Curl E is equal to 0. You see here on the slide, curl E is equal to 0. Okay, right. Here this is important. We may draw one more important conclusion from this mathematical statement showing the irrotational nature of the electric field. See, the curl E is equal to 0 is equivalent to the integral EdL is equal to 0. Why? Because if you go for the vector analysis, then you may convert that linear integral into the surface integral. When linear surface integral written in terms of the curl. Okay, this you may use Stokes' law here. So, integral EdL, linear integral of E is 0 means surface integral of curl E is also 0. That's why we have curl E is equal to 0 here. Whenever you have curl E is equal to 0, we may easily say that E is an irrotational field. Okay, this mathematical statement directly show the irrotational nature of the electric field E. See, one important conclusion you may draw by restating this mathematical formula, mathematical equation, curl E is equal to 0. See, whenever you express E in terms of the grad of some function, then what happens? Curl grad psi is equal to grad phi is equal to 0. So in vector analysis, you know that curl grad of something, scalar function, is 0. So whenever you write curl is equal to minus grad psi, it satisfies the above equation curl E is equal to 0. So you may restate this mathematical statement as E is equal to minus of gradient of the vector potential. Okay. So we may define a scalar function called potential for electric field. This facilitates us to define a scalar function called potential for the electric field. Okay. See, this statement curl E is equal to 0 or E is equal to grad phi, both are giving the same information about the field. See here, electric field and electric potential of an electric field gives the same information about the field. But there are some advantages. Of considering or defining the electric potential. Okay, right. Yeah, all of you know the electric potential. What is this potential? I already told you that it is an electrical work. Okay. See, this work is given by the potential. Okay, at upper limit and lower limit. For W is equal to, you got phi at A minus or phi at B minus phi at A. Okay. Phi at B, phi at A. So here you have to define Suppose you want to know the potential at A. For that, you desperately needed the potential at B, some other point. So, this potential can be determined up to an additive constant only. So, you have to fix potential at some point arbitrarily. By using that arbitrary value, you have to fix the potentials at each and every point of the electric field. That is what the difference between electric field and electric potential. Okay. How to solve this problem? So whenever you are taking the potential difference, the problem is solved. So instead of considering electric potential, we have to consider electric potential difference. Okay, this only will be meaningful. Then what happens? Undetermined constant will be cancelled. Okay, at point A and at point B. So the effect of undetermined constant will not be here if you consider the PV, potential difference, if you refer the 2 points in the electric field. Yeah. Finally, what is the potential of a point charge? What is the potential of a point charge? See, potential, I already told you that work means potential is equal to integral E dot dl. You have to integrate the electric field. Whenever you integrate the electric field formula of the point charge, then what happens? Minus of integral E dot dl or E dot dr. Okay, then what happens? You get simply instead of r square in the denominator, you will get r. So what is the formula for the electric potential of the point charge? 1 by 4 pi epsilon naught q by r. Instead of r square, you have q by r. So what is the formula of electric potential V? V is equal to here you see on the slide, V is equal to 1 by 4, q by 4 pi epsilon naught. Otherwise, you may write this is 1 by 4 pi epsilon naught q by r. You know this formula also. Okay, let us stop with this. In the next class, we will discuss about the relation between electric field and potential, okay, and some other topics. Okay, thank you.